Alright, so looking at number 12, we had the derivative of the natural log of 5 minus 3x plus x squared. The derivative of a natural log is 1 over what you're taking the natural log of, but then you need to use the chain rule, so it's times the derivative of what you were taking the natural log of. Alright, so that's where we get this 2x minus 3 over the 5 minus 3x plus x squared. Okay? We're just taking the derivative of this natural log of 5 minus 3x plus x squared. So, we prove then, or we show then that because of this, we know that the integral of this, okay, will equal the original function, the natural log of 5 minus 3x plus x squared, okay? But that's not the integral we were trying to find. We were trying to find the integral of when it had a 4x minus 6 in the numerator, not a 2x minus 3, okay? However, if you recognize that this is just 4x minus 6 is just 2 times that 2x minus 3, then I can multiply both sides of our equation by 2. And it's okay that this one's in the integral and this one is times that side because of the constant multiple rule. You can have the constant outside or inside your integral. Okay? So now, get that out of the way. Now we have the integral we were looking for, the integral of 4x minus 6 over 5 minus 3x plus x squared dx. Okay? And that equals the natural log of 5 minus 3x plus x squared squared. If you remember your rules for logarithms, when you have 2 times a log, you can bring that up as the exponent, okay? It wouldn't be counted wrong if you had left the 2 out there, but just to make the connection there. Now, the reason why I wanted to point that out specifically is because today what we want to look at is kind of summarize some of the rules that we've already been using, but also to introduce 3 new rules. And one of those rules is when you have the integral of 1 over x dx. Okay? Someone explain to me why we can't just make that x a negative 1 and then use the rule we've been using.
Because it ends with the coefficient equaling 1 over 0.
Exactly, okay? You add 1 to the exponent, now you have x to the 0, and then you're dividing by 0, and that's undefined. Okay? You can see here, though, even though we don't have 1 over x, you can see here we had 1 over something. Okay? And you'll notice here we ended up with a natural log. Okay? So that's kind of the connection I want you to make, because one of the rules that we're going to use today is this, and I'll just give you the rule now, we'll see it again in a moment. The integral of 1 over x dx is the natural log of the absolute value of x plus c. Okay. Now, you can kind of see the connection here with this problem. Obviously, the problem we did is a lot more complex than just a 1 over x, but you can kind of see the relationship. We've got 1 over something, we end up taking the natural log of that. Okay? So, we'll revisit this in a few minutes, but I wanted to make that connection before we moved on. So, oops, wrong one. So let's take a look at a summary of the rules for integration. This actually covers the specific rules that you'll need to be able to use and know for your IB exam. But we have, first of all, the integral of a constant. Okay? The integral of a constant. And they're showing you to the left here, using the derivative, how we can come up with this rule. But if you think about this, a constant k is the same thing as if I wrote k times x to the 0 power. So now if we add 1 to our exponent and divide by the new exponent, we're doing k times x to the first over 1, which of course is just kx. Alright, so when you have a constant, the integral of the constant is the constant times x plus c. A second rule, we've used this one a lot, so I won't spend much time on it. Second rule is for x to the n power. We have x to the n plus 1 over n plus 1. You guys know that one pretty well by now. Okay. Another one, this is a really nice one, e to the x. You guys know the derivative of e to the x is e to the x, so the integral of e to the x is e to the x. Okay? Now we're getting to our three new ones. Okay? Our three new ones, if you notice your derivatives, okay, your derivative of the natural log when x is positive or negative, both end up being a 1 over x. Okay? Now, because it can be positive or negative, we use this absolute value, okay? Or you might see it called the modulus, okay? So we have the natural log of the absolute value of x. This is the one case that our x to the n power doesn't handle, okay? Is that x to the negative 1, or 1 over x. So we have the natural log of the absolute value of x. Okay. Now, one of the reasons why we need that absolute value in there is because you can't take the natural log of a negative number. Think about it. The natural log gives us the exponent of e that will give us what we're taking the natural log of. Okay? Well, I don't care what power you raise e to, it's never going to equal negative 1 or negative 5 or anything else. Negative. Okay? So you can't take the natural log of a negative number. That's why we need these absolute value symbols. You'll notice over here, they're doing the natural log of negative x, but notice x is already negative. So you have a double negative. You're still taking the natural log of a positive over here. Okay? We have to do this here. You might say, well, why don't we just, why do we even have to put it in there? It's because in the original function, 1 over x, x was defined for everything except 0. X is defined for anything except for 0. So since the original function has it defined for negative numbers, we need our integral function, the natural log, to be able to handle those negative numbers as well. Okay, does that make sense? So we put the absolute value in there, so any negatives from our original function are made positive. Okay. All right, and then our last two. When we were looking at the homework problems, we also saw one. not that one. We also saw one where we were working with sine and cosine. Okay, cosine. Or I'm sorry, when we took the integral of sine, it was originally, we have sine of 2x. We ended up with a negative 1/2 cosine of 2x. So you'll notice here, when you're taking the integral of sine, it actually ends up giving you a negative, and you get a cosine. All right? And that's actually one of our rules for today. Okay? The integral of cosine is a positive sine plus c. The integral of sine is a negative cosine. Okay? Now, it's really easy to get these mixed up, which ones end up negative, which ones end up positive, and so on. Alright, so Mrs. Barbag actually has a real easy way of remembering this that she showed the AP class. I thought was cool. So sine, cosine, negative cosine. If you can remember that, then you can remember all your derivatives and integrals. Okay? The derivative of sine is what? Cosine. The derivative of cosine is, what's the derivative of negative sine? Negative cosine. What's the derivative of negative cosine? Positive sine. Alright? So if you go this way, when you're differentiating, okay, you can go the opposite way when you're finding the integral. The integral of cosine is sine. The integral of sine is negative cosine. Okay? So it's a nice little trick. It really takes no time at all to write that down, and then it just helps you make sure you keep your positives and negatives straight. Okay? It's easy to mess up. Alright, so let's practice a couple using some of the new rules that we have, and then we'll look at one additional item here. So let's start. It says integrate with respect to x. We have 2 sine x minus cosine x. Alright, so anytime you're asked to do this, make sure you write down the original problem. So we have 2 sine x minus cosine x dx. So, notice how we're going to use the rules that we proved yesterday. Here we have the difference of two functions, and we have a constant multiple. Okay? So we can handle those by, first of all, I'm just going to deal with the 2 sine of x first. And while I'm dealing with 2 sine of x, I can just write down the 2, because it's going to be 2 times whatever the derivative of sine of x is, or integral of sine of x is. Okay? So what is the integral of sine of x? Negative cosine. So we have a negative 2 cosine x. Alright? Now, minus, now we can deal with the cosine. What's the integral of cosine? Sine. Okay? Plus c. Alright? Alright. Do that if it helps. Alright, so notice here we actually had a minus cosine. The integral of minus cosine is minus sine. Okay? So there's our integral. Any questions? Comments? Anything? Okay. So now we have the integral of negative 2 over x plus 3e to the x. Again, we're going to use those properties. Okay? And really, if you break it all the way down, I didn't do this with the previous one, if you break it all the way down using our properties, you could rewrite this whole problem as this. Negative 2 times the integral of 1 over x dx plus 3 times the integral of e to the x. Okay? So, once you break it down there, then it's just a matter of, okay, what was that rule? What's the rule for 1 over x?
Natural log of the absolute value of x.
Good, natural log of the absolute value of x. So it's negative 2 times the natural log of the absolute value of x. Okay? Then plus 3 times, what's the integral of e to the x? E to the x. And then of course, the constant of integration, the plus c. Yes?
Okay, so I'm, not this last step, but the one before, I'm very confused as to how you broke that up.
Okay. So for this one, doing the same thing that we did here, we could have broken this down into a 2 times the integral of sine of x dx, okay, minus the integral of cosine of x dx.
Okay,
Okay, so now
okay, that makes sense.
the integral of sine is negative cosine.
Right.
The integral of cosine is sine.
Okay.
And guys, if it helps you to write it out this way, you know, do that. You know, don't, until you get the hang of it better, write it out a little more. It's better to write a little more and get it right than to just kind of guess. Okay.
And these rules are in the formula booklet?
The formula booklet has, I know it has sine and cosine, it has, here we are. Actually, how many of you did not get, I had handed out just the calculus page from the formula booklet. How many of you were not here the day I did that? Anyone?
Jordan, I don't think you were here. Yeah, I have it.
Alright, so your integrals, they give you x to the n, they give you 1 over x, they give you sine, cosine, and they give you e to the x. Alright, so basically, they don't give you the constant. That's the only one that they don't give you, but like we said, that's kind of like the x to the n anyways. Alright. Alright. So, one of the challenges with integration is the fact that there really is no product rule, or quotient rule, or chain rule. And you might say, well, that's not a challenge, that's a blessing. Well, it kind of is because you have fewer rules to learn, but there's a lot more problem solving that kind of goes into finding integrals. And in fact, there are, while with derivatives, there were cases where the only way to find your derivative was to use that definition with the limit as n approaches 0 and so on. With integrals, there's a lot more cases where the only thing we can do is approximate it using those rectangles like we did the first 2 days, okay? Now, once you get to that level in dealing with those types of functions, you actually don't use rectangles anymore, we use trapezoids because it gives us a better approximation of the area. But, because there aren't product rules, chain rules, quotient rules for integration, we have to do certain things when we're finding integrals that we didn't have to do with derivatives. For example, here are 2 examples. where as they're written, we can't find the integral, although we don't need any new rules to find these integrals, okay? For example, in this case here, the integral of 3x plus 2 over x quantity squared. In order to integrate this, there is no chain rule to help me handle all this. So what I have to do is actually first expand the product. I'm going to have to FOIL it out. So we have 9x squared plus 3x times 2 over x. The x's will cancel, so it's just a plus 6. And we've got 2 of those, so it's a plus 12 plus 4 over x squared. I know you guys can FOIL, so if you don't follow that, you can do it again later. So we actually FOIL this out, and we get 9x squared plus 12 plus 4 over x squared. So now we have a much simpler, now we basically have a polynomial that we're dealing with, okay? And we can break that down using our properties if we want. So 9 times the integral of x squared plus the integral of, I forgot my dx, plus the integral of the constant 12 dx plus 4 times the integral of 1 over x squared. Now that we're not going to use a natural log for that, it's going to be x to the negative 2 that we're treating it as. Yes?
So you just took the 9 out for the first part?
Yes. I split this up using our property we looked at yesterday where we have the sum of functions that we're taking the integral of. You can separate that into 3 separate integrals.
Okay.
You don't have to. If you can see it without writing it all out, you can do that, but just showing you what you'd be doing at least in your head. So now we have 9 times, what's the integral of x squared?
No. 1/3 x cubed.
1/3 x cubed, okay? So now we have a 3x cubed, okay? What's the integral of 12?
12x.
12x, okay? So we'll bring that down. And then plus 4 times the integral of x to the negative 2.
-4 over x.
Okay. The negative x, or x to the negative 2, add 1 and you get x to the negative 1. Okay. Times, or divided by the negative 1 is a negative x to the negative 1, and that does give us a minus 4 over x. Okay. So, that would be plus c. That would be our final answer. Okay? But we couldn't do that without foiling it out first. Okay? Are there any questions about any of those steps in there? Yes.
Could you just remind me how you got x to the third over 3?
This was our rule for the x to the n. So since it was x to the third, or x squared, we add 1, so it's x to the third, and then you divide by the new exponent. Sure. Okay. Anything else? Okay. Then we have a case like this. We have the integral of x squared minus 2 all over the square root of x. Well, this is a case where we don't have a quotient rule, but because our denominator is just a monomial, we are able to kind of distribute or split apart your fraction into 2 separate things here, okay? we're going to deal with x squared over the square root of x minus 2 over the square root of x. Okay? We split it up into two fractions with that common denominator. Okay? Now, we are going to want to reduce this first fraction. Okay, so that we're going to be taking the integral of x to what power?
1.5.
Yeah, 1.5 or 3/2. Either way you want to write it. Okay? 2 minus 1/2 is 1.5. So we're taking the integral of x to the 3/2 and then minus 2 times the integral of, that's just x to the negative 1/2. Thank you. Okay, now we're just dealing with our x to the n rule. Okay, so we add 1, it's x to the 5/2, divided by 5/2 is times 2/5. Okay, then we do a minus, this is going to be x to the positive 1/2 now. When we divide by 1/2, that's multiplying by 2. So that 2 times this 2 gives us a minus 4. Okay. So, we can get past not having a chain rule and not having a quotient rule in cases like these, okay? Notice here's where knowing your binomial expansion can be helpful, because if this were to the 4th, still the only way you'd be able to integrate it would be to multiply the whole thing out. So, alright, so what I want to do, we don't have homework for the weekend due to the holidays, but I want to give you some time to practice with some here in class. One thing to note, the book is inconsistent in the back of the book as far as how it gives its answers, and I think they're just, at least in the, I haven't checked the hard copy, but at least in the PDF version of the textbook, sometimes they're missing the absolute value symbols when they have the natural logs, okay? Those are not optional, alright? You do need the absolute value symbols. There are a couple cases, like for example, in D, since you had the square root of x, x couldn't be negative anyways, but we would still put in the absolute value symbols when we did the integral of 2 over x, okay? So even if the book does not have the absolute value symbols around or in the natural log, you should have them in there. Okay. Some of the spots they do, some of the spots they don't. I don't know if it was when they converted it to a PDF, if it didn't render those or what the case was, but you should have them. Alright, so I'm going to give you guys the remainder of the time to work together on these, practice these, try to really keep in mind what rules you're using, and get comfortable dealing with finding these integrals, okay?